Hello! I published quite a few repair videos lately, but now I think it's time to build something. I prepared quite a pile of parts here. Look at this. Recently I got myself a used Nissan Leaf. It was a great deal, and for about 2 months I'm driving on electrons, and I'm quite happy about it. For the most part I charge at work for free, but if sometimes I need to charge at home, the car goes with this level 1 charger, and level 1 means it plugs into a regular outlet, which here in the United States is 120 volts up to 15 amps, and this charger is limited to 12 amps in fact. So it takes quite a long time to charge. Back to our pile of parts. So I decided to build myself a level 2 charger, which will charge much faster, and for this I'm going to follow an existing design, open hardware and open software project called OpenEVSE. There is a website for the project with all the schematics and software and build guides and such. However, I believe it can be quite challenging for beginners, so I will build this thing from scratch, not using any kits they sell, and explain in detail exactly how it works. A bit of warning: this project involves high voltage, high power, so if you are going to attempt something like this, please take time to learn, make sure you know what you are doing, or get help. Let's make it fun and not get hurt. Here is the main page for the project, which is hosted on Google, and this picture is of a pre-assembled board which they sell in the store. Let's have a look. So here they sell a few versions of a kit, and in this section there are 4 versions of the kit with enclosures and 2 versions without enclosures. This is the simplest one with no LCD. This one I believe has color LCD. This version has 50 amps capability, and because of that only supports level 2, no level 1 support here. And these kits don't require any soldering skills, just general assembling and crimping of wires at most. What is also needed to finish the project is a cable to a car with connector, and they also sell all kinds of parts like fuses, relays, fuse holders and such. They also sell boards separately, 2 versions, version 2.5 and version 3. So let's go back to the project page. Here in the wiki section they have all the documentation. In particular they talk about theory of operation here, describing all the systems, how they work exactly. And here are the build guides, and we are going to look at this do-it-yourself EVSE Plus. Here they describe what roughly corresponds to a basic combo in the store. And here's the link to all schematic diagrams and such. But firmware, if you want to program the microcontroller, is in the store, which is slightly confusing. Let's go back to the store for a moment. And if we go into this basic combo, here you can get the zip file in which there are all pieces needed to program a microcontroller. Let's talk about the theory of operation, and let's briefly cover electrical service connection. This is a typical connection to a house in the United States. From the utilities we are getting 3 wires, 2 hot wires and 1 neutral. And the neutral is bonded to the ground, and there is 120 volts between each hot and neutral. And the typical outlet in a house is connected to neutral and one of the hots. So some outlets connected to one hot, some other outlets to another. And this is 120 volts, 15 amps outlet. And of course this is very much simplified. There is electrical panel and the meter, and each hot is connected through appropriate breaker, in this case 15 amps breaker. And this is a typical electrical dryer outlet. This is an older standard with 3 wires. There is a newer one with 4 wires, which includes neutral. This older one includes only 2 hots and the ground. And that's all we need. This type of connection we need for our level 2 charger. 240 volts, 30 amps. And of course in this case both hots are protected by appropriate 30 amps breakers. So here I found a picture of outlets for dryers and ranges. So in my house I have this kind, and as I said there are 2 hots and the ground, and this is a newer one, in which case we have hot, neutral and ground. And for our purposes, for level 2 charger, we don't need the neutral ones. So if I had this type, I wouldn't connect the neutral at all to our charger. And the reason I'm talking about dryer outlets, because it's the easiest way to get started. Typically they are located in garages, but not always. In my case I have a little laundry room in the house, so I will need to run a little extension from there to the garage. And later I will work on having a dedicated cable to the garage from the electrical panel. Let's move on to our charger. And the charger is in fact quite simple. Yes, a microcontroller is involved. However, all hard part is happening in a car. And by hard part I mean high voltage, high power conversion and regulation and whatever is necessary. It's all in a car. Charger is essentially pass through with respect to high voltage, high power lines. On this side we have our connection to the electrical service, whatever it is, hardwired connection to electrical panel, or a plug to an outlet, which can be a dryer outlet or range outlet or regular 120 volts outlet, in which case it's going to be level 1 charger. It supports both level 1 and level 2. And on this side we have our J1772 connector to a car. As you can see, all we do to our 2 power lines is some protection and switching. And the microcontroller is talking to a car using this one line called pilot, and does a little more protection and sensing. We will talk about this later, one thing at a time. I added a few things for completeness here. First of all, power supply. It's connected to the ground and both lines after the fuses, and it is providing 5 volts for our microcontroller and plus minus 12 volts for the pilot signal. Next, our microcontroller is driving relays, and as I said, it can be one relay or contactor or 2 separate relays. Having 2 separate relays is better because the controller can do a self-test connecting one line at a time and therefore not energizing the output completely. Next, we have 2 sensing lines. The controller is sensing voltage after relays through optocouplers, and this is used for detecting if it's level 1 or level 2 connection to the service, and if relays are working properly. And next we have a current sensor measuring current flowing through these 2 wires together, and this is called GFCI, which stands for Ground Fault Circuit Interrupter. And that's all there is to it on a high level. So let's discuss some details one part at a time. Let's talk about the power supply first. OpenEVSE design uses this monolithic module, and this module is supposed to receive from 100 to 240 volts AC, and it delivers 2 rails, 5 volt rail at 120 milliamps maximum and 12 volts rail at 250 milliamps maximum. And the negative rail is made from positive 12 volts using this DC to DC converter, and it's mounted here on the board. And this solution is quite nice and compact. Currents this thing delivers are not much higher than is really necessary, so it's quite hard to get it more compact than this. However, this module, I believe, is not very easy to find. For example, I couldn't find it at both suppliers I use all the time, which are digikey.com and mouser.com. I shopped around and I found these 2 power supplies at our local electronics store, one of my favorites, called Weird Stuff Warehouse. Yes, these are not as compact as OpenEVSE design uses, but they are very cheap, $5 each, and they provide all 3 rails. This one is Cisco Systems, model is ADP30RB, and it provides 5 volts at 3 amps, positive 12 at 2 amps, and negative 12 at 0.2 amps. And this one is even more powerful. The model is ACE 890A, and the output is 5 volts 10 amps, positive 12 at 2.5 amps, and negative 12 at half an amp. And this is way more than necessary. And an important part here is that in order to support level 1 and level 2, the power supply must be switching supply, so it can automatically support wide range of the input from 100 to 240 volts without any need to flip a switch. And one more point I would like to emphasize, which can be confusing to some people, about the input. Usually it's marked like so: earth, neutral and line, or something like that. And we should understand that there is nothing special about this neutral at all. If you look at schematic diagrams of typical power supplies, both lines are completely symmetrical. There is no difference. You can flip them around. And in our case, we are even going to connect both to hot lines, each of which is 120 volts with respect to earth. And there is no problem with that at all. As soon as supply supports a wide range of input, and it does, I found the specs for this supply, and here we are. Input 85 to 264 volts, no problem at all. Now let's talk about this J1772 connector to a car. This is by far the most expensive part of the whole charger. The cheapest new one I saw on eBay was $120 with shipping. So I shopped around and found this used one on eBay, which was $80 delivered. And pay attention, some of them are rated only for level 1 chargers, which means they don't support 30 amps. This one is rated at 30 amps, and the wires here are 10 gauge, so here it is 10 gauge AWG by 3. And here we are, 3 10 gauge wires plus that smaller pilot. Now let's talk briefly about our dryer connection. I found this 4 feet dryer cord on eBay for $10 delivered. At a hardware store this can be easily more than $20 with tax. And I am going to use these, so I'm going to mount this outlet to the end of this cord, and the charger will plug in like this. And again, $5 each at Weird Stuff Warehouse. These can easily be more than $20 each at a hardware store. And if you are going to use something like that, pay close attention. These should be rated at 30 amps, 250 volts. There are all kinds of very similar looking ones. Some of them are rated 20 amps only. They are slightly smaller diameter. Some of them are rated at 30 amps, but 120 volts. And it's not only rating, the pin configuration is slightly different, which is not immediately obvious. Some of them have this notch to the outside, not inside. I am going to use this fuse holder, which I found used on eBay, very cheap. The model is BM6032PQ, and they exist with different letters at the end, indicating the type of terminals. So this PQ means pressure plate bolts, and these quick connect terminals as well. And the fuses must be 30 amp slow blow fuses. And we also need a ground bar, something of this kind. I bought these 2 separate relays on DigiKey, exactly the same type used in the OpenEVSE project. And here is the GFCI current transformer for measuring the current flowing to the output. Let's talk about this GFCI protection for a moment. The idea is quite simple. In normal circumstances, current flows through one wire, through the load, and returns through the other wire. And if we measure overall current through both wires using a current transformer like this, we should measure 0. If there is a problem, let's say some isolation is broken in the load, and I touch that spot and some part of the current starts flowing through my body to the ground. In other words, we have a ground fault. This means some part of the current will not return through the other wire, and we will start measuring some difference here. As soon as that difference exceeds some threshold, the protection should kick in and disconnect the power. So let's talk about this pilot signal. The pilot signal is a way for chargers to advertise how much current they can provide, and this is done by setting a duty cycle, which means the proportion of this positive pulse to the whole length of the period. And the way I drew it here, the duty cycle is 50%, which corresponds to 30 amps. But in fact, the basic model is limited to 24 amps, in which case the duty cycle will be set to 40%. So let's consider initial power up. Charger is powered up, car is not connected. Charger will go through some self-test, determine everything is good. So it will start advertising, let's say 24 amps, by putting out this plus minus 12 volt square wave of 1 kilohertz frequency and 40% duty cycle. Then we plug in a car, and the car will apply some load to the positive side of the wave, which means connect a resistor and a diode. And that is done for protection, to distinguish normal situation and an error when, let's say, a charger is mounted outside and the connector is dropped into a puddle of water or something like that. So the car connects a resistor through a diode, and this positive pulse voltage drops to 9 volts, and this state means vehicle is connected and ready to charge. Another state is when a car applies slightly smaller resistor, again through a diode, so that voltage of the positive pulse drops to 6 volts, and this state is charging. At this point, the charger should connect both relays, and charging starts at this point. When the car is charged, it goes to this state and the charger disconnects the output. Alright, let's start building this thing up step by step. Here I grabbed 80 mega 328p and arranged absolute minimum around it. Connected the power supply, only 5 volts for now, and we can turn it on and off here. Here is the reset button. I connected the 16 megahertz crystal and 22 picofarad capacitors for the crystal, and 3 LEDs which are ready, charge and error. Also, these are bypass caps on 5 volt rail, and this capacitor is, let's look here on the schematic, it is this one, C12 on analog reference. And here on the schematic it is Mega 8, which is different from what I have, so I wrote these corresponding pin numbers on 80 mega 328p. And LEDs are supposed to be green, blue and red. Instead of the blue one I put yellow one. I don't have blue one handy at the moment. And I'm using schematic for version 2. I chose this one because this version still has LEDs connected directly to the microcontroller. Version 3 has LEDs on a separate board connected through I2C interface, and that's a complication I don't want to deal with right now. I programmed firmware into the 80 mega, And there are many ways. I used this Mini Pro USB programmer. They are quite cheap on eBay. So, what do we expect from this minimal setup? I expect it powers up and starts self-test and shows error. Let's try this. There you go, it shows an error. So, why do we see the error? Well, because self-test fails. And this self-test includes 3 things, I believe. One thing is reading what's on the pilot line, and it's not connected right now. Another thing, it tries to drive relays and then sense these line voltages. And third thing, and I just added this coil here, it was not on this diagram before. This is a clever way to test a GFCI. So a few turns of wire are added to this transformer to simulate some non-zero reading on GFCI. So it tries to put a pulse into this coil and then read the fault from GFCI. So, and this thing is very easy to simulate. We can just put a jumper across these 2 microcontroller pins. They are both positive, so the positive pulse here should produce positive response here. So let's do that and try. Alright, I installed this jumper between pins 12 and 4 to simulate working GFCI. So now we see blinking error, as if it stepped a little forward from that previous state. The next thing I propose to do is try to pretend that pilot works. So here is the op-amp responsible for plus minus 12 volt pilot signal, and the input to this op-amp is called PWM. It comes from this pin on the microcontroller, and this plus minus 12 signal is scaled back here to the 0 to 5 volt signal and is read back here on pin 24. So I propose to just put a jumper between these guys, so the positive pulse here will produce positive 5 volts here, and we'll see what happens. So here I installed this jumper to pretend that pilot works, and let's try now. So now we see the charge LED blinks for a moment. Let's try again. So we made a little more progress. Charge LED is connected to one of the relay drivers. So what it's trying to do, it is trying to drive the relays and sense the AC lines here. So we should simulate at least one of them so that it can decide that at least level 1 is available. And it's not straightforward to simulate that with a jumper, because this is the negative response. Let me show you on the schematic. So here are the opto-isolators. IC lines are connected here, and the output is this line, and once AC is connected, this output is driven low to the ground. So it's impossible to just simulate it with a jumper from the relay driver to this output. We need to invert that relay driver. So I will install one of these guys and we'll see what happens. Let's have a look what's happening inside of these optocouplers. There are two back-to-back LEDs on one side, so that polarity of the input doesn't matter, and this transistor drives the output to the ground. So here I installed one of the optocouplers and I put LED on the output so that when the output is driven to the ground, LED will light up. And the input I connected through 2.7 kilo ohm resistor to this wire, and I'm going to attach it to the positive 5 volt rail. So that's enough to make this thing work. So I will attach this input to the relay driver. So here I connected the input of the optocoupler to the relay driver pin and the output of it to the pin which is supposed to read its status, and let's give it a try. There you go, it goes to ready state. So what's next? I think I need to build a proper pilot circuit so we can check out what's happening there. Here I assembled the pilot circuit and I attached 12 volt rails here and prepared a diode and resistor to simulate a car connected, and this is the pilot output. So let's connect it to the car, and there you go, we are in the charging state. And perhaps because 12 volt rails here are slightly lower, instead of plus minus 12 I have plus 11.6 and minus 11.4 or something like that, and perhaps because of that I had to adjust one resistor here. So this 200 kilo ohm resistor, I had to put 150 kilo ohm here before it started working properly. So I suspect that this output of the pilot, in particular this resistor network and such, is sensitive to power rails being very close to 12 volts. I should probably try with another power supply. Let's check out the pilot. So here I connected the scope to the pilot output, and here we are, 1 kilohertz and 20% duty cycle. And why 20%? Well, because 20% corresponds to level 1, 12 amps. And this is because I only connected one sensor. So when charger does the self-test, it tries to connect both lines and only one responds. So it believes the other one is neutral, so we have level 1 connection, and therefore it advertises only 12 amps. So let's put a jumper and pretend that during that self-test both channels respond, as if we have two HOTS connected. So we should see 40% duty cycle. I put a jumper between pins 5 and 6 to pretend that both lines are hot and our connection is level 2. So the charger started advertising 24 amps. As you can see, the duty cycle is 40% now. And now I'm testing with Cisco power supply. It seems to be more precise and everything works fine with no adjustments at all. And it's easy to take apart. There were a couple of screws hidden underneath this rubber fit. And slightly tricky part is that this wire marked ROF needs to be connected to the ground to enable the output. It's been a few days since I started recording this video, and in the meantime I found a few more options for power supply. I'm trying to come up with a more compact solution, especially if I'm going to build a portable version. I'm not sure yet. I didn't get an enclosure, so I didn't decide yet if I'm going to build a portable one or a bigger one which can be mounted on a wall in the garage or something like that. So first of all, I received a couple of these isolated 12 volt to 12 volt DC to DC converters. So because it is isolated, it can be connected to a positive rail, 12 volt rail, and produce negative 12 volt rail. This is very similar to what is used in the OpenEVSE design, but not quite the same. And the current it can provide is tiny, maybe around 80 milliamps maximum or something like that, but we don't really need this much. So it should be perfectly fine. So, and because we can make minus 12 volt rail easily from positive 12 volt rail, now we don't need the power supply with 3 rails. So I found this one for a couple of bucks, and they have tons of them. So this small power supply is again switching power supply with wide range input from 100 volts to 240, and it produces plus 5 volts and plus 12 volts at amp each, I believe. There is that sticker on that capacitor explaining all this. So this gives us more compact version. Compare it to the Cisco power supply. So this thing can be mounted on a board, and this thing is quite a bit smaller. And one more option, because we don't really need a lot of current on the 5 volt rail, I thought it should be possible to use something like classic 7805 regulator to produce 5 volt rail from 12 volt rail. And on the 12 volt we need more current, because relays are powered from this 12 volt rail, so we need a couple of 100 milliamps at least. But on the 5 volt rail we probably need something like 20 milliamps or so, especially with basic version when we don't have LCD and other loads. So we only have microcontroller and a few op-amps. That should be around maybe 20 or 30 milliamps maximum. We can measure that later. So in this case, if I can make 5 volt rail from 12 volt rail, we probably will need a tiny heatsink, because it's gonna drop 7 volts. Even at this small current it can get a little warm. So if we can make 5 volt rail using this thing, so we can use something like that for 12 volt rail. And I found a couple of these for $3 each. The same place, Weird Stuff Warehouse, and this again is switching supply, 12 volt, 1 amp, with the same 100 to 240 volts input, and this is Linksys Very similar. Current is slightly lower. I don't see it now. It's half an amp. That should be more than enough. So the only small problem that they are not assembled using screws or anything like that, so you need to really break them open. But that's just a minor thing. So for example, this thing, all this part I believe is a connector, so inside we should see a small board like this and compare it to even that supply. So it should be even smaller, and 5 volt and 12 volt, negative 12 volt will make from that. So should be another good option for a portable version. I will stick with this option for now, with this DC to DC converter, and this option with the 5 volt regulator I will consider once I get some enclosure, and if I happen to need more space in it, then I will see if I need to break one of these apart. And this is an alternative to 7805. It's gonna drop 7 volts in this configuration, and even with small current can get hot, and it's not a very good idea in completely sealed enclosure. So this might be a good alternative to it, because it's a switching regulator. It can do up to half an amp without any heatsink. I didn't order this one yet, and probably I'm not going to need it, but just to show you that there's a good alternative. It's not very cheap, it's about $5.50 on DigiKey, but could be a good idea if you are looking for a compact solution. Here I built this up on a Vera board. And I left some room for potential modifications. This connector is for LEDs, and I printed labels on these connectors. And here I didn't want 240 volts to be very close together, so I used 3-pole connector and removed the center pin. Perhaps it's a bit paranoid. Here I mounted everything on a piece of plywood, and I made this level 1 adapter. So let's give it a try. Plugged in, let's go. Alright, relays are clicking, self-test passed. Let's try with the car. Trying level 1 first. The charger is plugged in and ready to go, and I plug it in through this kilowatt meter to measure amps. Let's connect the car. Alright, around 12 amps, as it should be. No problem at all. Now let's try level 2. So I've built this dryer outlet adapter, and I also have this extension. Again, same place, just $20. Let's go. Alright, I connected to dryer outlet and set up this clamp meter to measure the current. 1 millivolt per 10 milliamps. Let's connect the car. Alright, everything works, but the car takes about 16 amps,
which is a bit disappointing. I was hoping to see about 24. Let's check the duty cycle. Okay, I set up this fluke to measure the duty cycle. 40%. So the charger is advertising 24 amps, but the car is taking only 16. I don't know why. It's a bit disappointing, but it's not the charger's fault. The car shows level 2 charging, 240 volts, and I charge to 80% usually to improve battery life. I don't really need the full range. I declare success. This 16 amp thing is a bit disappointing, but it's not the charger's fault. I don't know why the car is not taking more. I don't have an enclosure yet. I will look for some enclosure and maybe we'll post a follow-up. Thanks for watching. Bye.